part B, so it's worth 25 marks. And if you have a read down through it, you can see it's a little bit more abstract than what we're used to, in that they don't give us specific reactants and products. They've kept it general with gas A, gas B, gas C. But as we go down through this question now, you'll see that actually it doesn't really affect our calculation. Everything we are going to do is the same as what we've been doing in the other questions. So don't let that throw you off. So the first thing that they do is give us the equilibrium constant. So we're told the equilibrium constant is 4, and we've got a 10-litre container, and we're told that we start with 30 moles of gas A. Calculate the number of gaseous moles at equilibrium in the container. Now, this is a different way of asking it in terms of our final answer, but how we tackle it is exactly the same. So what we're going to do is we are going to just rewrite that equation here so that we can set up our little table. We're going to have our first row as concentration at, not at equilibrium, our initial concentration, and we want that in moles per litre. We're going to have a row to track the change, and we are going to have a row for our concentration at equilibrium, also in moles per litre. So they tell us that we've got 30 moles initially of gas A, but we know that's in a 10-litre container, so we're going to divide that by 10, and that's going to give us an initial concentration of A as 3 moles per litre. And we know initially we have 0 moles per litre of B and 0 moles per litre of C because they are our products. That's all they give us, apart from giving us the Kc equal to 4. So at this point, again, it looks like we don't have enough information to continue, but I promise you we do. We're going to introduce an x as our unknown. So we don't know how much our gases change by, or the concentration of our gases change by, but we can introduce an unknown and figure that out using our Kc. So we're going to say, okay, our gas A will change by a concentration of X. So X amount of it will decompose into B and C. So this is a nice equation because it's a 1-to-1 ratio. So that means that if X of A decomposes, it's going to produce X of B and X of C because it's a 1-to-1 ratio. So now I can complete my table. My concentration of A at equilibrium is 3 minus X. My concentration of B and C is X. Now what I can do is put that into my Kc equation. So let's write that Kc equation first of all. So I've got B, concentration at equilibrium in moles per litre of B, raised to the power of 1 for each of those because the coefficient of each of those in their equation is 1, divided by the concentration of A at equilibrium. So I can put those numbers in now. I've got X, or X, divided by 3 minus X. And I know that that is equal to 4. So once you rejig this around, you're going to end up with an equation in X. So we've got X squared plus 4X minus 12 equals to 0. And when you solve that, you end up with X is equal to 2 and X is equal to minus 6. Now, how do we figure out which of these numbers we're going to take? Well, if we have a look at X is equal to minus 6, if we were to put that back into our table, that would mean that the concentration at equilibrium of B and C is minus 6 moles per litre. Now that can't happen. If we started off with 0 moles of B and C, we can't end up with minus 6. We can't lose concentration that we didn't have in the first place. So that value for X does not make sense, which means that we're going to take our value for X to be 2. Now, the question is phrased slightly differently because we're used to them asking us for the concentration at equilibrium of the reactant or the product. But what they've asked us for is the total number of gaseous moles at equilibrium in the container. So the total number of moles is actually adding up all the number of moles of A plus B plus C. So that's basically saying if we take our concentration at equilibrium, we've got A, which is 3 minus X, plus B, which is X, plus C, which is X. We know that X is equal to 2, so 3 minus 2 is 1. So we've got 1 plus 2 plus 2, and that gives us a total number of moles of 5. Now that's moles per litre. The question asks us in the container, so we had to convert to moles per litre to work down through that table, but the final answer needs to be in relation to that container. So that's moles per litre. In the 10 litre container then, we just have to multiply that 5 by 10. So that gives us a total number of gaseous moles of 50. So it's a funny way of asking it. And you really need to make sure you're reading the question to recognize that. Okay, so let's have a look at the next question. The graph shows the relationship between temperature and Kc. Okay, we'll just zoom in for a second. Deduce whether the dissociation of gas A is exothermic or endothermic and explain your reasoning. Okay, I might just redraw that down here so that we can scribble. So here's our graph. We've got Kc and we've got the temperature. And we can see that we've got this curve. Now what that curve is showing is that as temperature increases, Kc also increases. Okay? And if we think back to what Kc really is, it's our products over our reactants. Okay? So if Kc is increasing, that means that the number of moles of my products is also increasing. Okay, so if Kc is increasing, the moles of products are increasing, which means the forward reaction is being favored. If the forward reaction is being favored as the temperature increases, we know that as we increase the temperature, according to Le Chatelier, if we increase the temperature, the endothermic reaction is favored. So as we increase the temperature, the endothermic reaction is favored. So if we've got an increase in Kc as the temperature increases, that means that the forward reaction is endothermic. So the question asks us about the dissociation. So we have just figured out that the forward reaction, which is the dissociation, is endothermic. So therefore, our dissociation is endothermic. Okay. And the final question, if we go back, explain how an increase in the storage temperature would affect the pressure of the equilibrium mixture. Well, we have just said, let me just write storage pressure here. We have just said that as the increase in temperature occurs, the forward reaction is favored. So we've got A being produced or being decomposed into B plus C. So if the forward reaction is being favored, we've got more of B and C being produced. So that means that the pressure is increasing. So how are you going to write that? We've just figured out that as the temperature increases, we've got the forward reaction being favored. So if the forward reaction is being favored, we've got more moles of B and C produced, which is going to result in an increase in pressure. So that was a nice little question for 25 marks. More abstract, as I said, than what we're used to, but very, very doable.